Let's say you're going to put a satellite into space and you need to know where it's going to be, or you want to know where a planet is going to be around the sun. You need to know its orbit. Now, here I've drawn a picture of an orbit. Here you have the orbit thing, and I'm going to define the shape of the orbit here. Now here is the planet, poorly drawn, but okay. And this large line is the major axis. Half of that is the semi-major axis, A, denoted A. And then the lowest point closest, or the point closest to the planet is the periapsis, and the point farthest from the planet is the apoapsis, which isn't really relevant to that right now. Now, to determine the eccentricity, which is the sort of the squishiness factor of the orbit, you need to know the semi-major axis, and then this thing here called the linear eccentricity. Now that is simply the distance from one focus to the center of the ellipse. And then you divide the linear eccentricity by the semi-major axis, and the linear eccentricity is here, C. So you divide C by A, and you get E. Now that's the shape of the orbit. Now other types of orbits, all orbits are conic sections. So here, a conic section is just the slice that a plane takes out of two cones together like this. So if this is one cone, here, this is a cone here, the slice out is the conic section. Now, first you have a circle. Now that is pretty boring, no eccentricity, it's just a flat cut out. Here you have an ellipse. Now that is a bit more interesting, it's still complete, but it's at an angle to the rest of it. Now to determine the eccentricity, you take the angle that the cone is at here, you take the sine of that angle, I used B as the variable for that, take the sine of that and divide that by the angle that the ellipse is cutting at relative to, I guess what you could call the bottom here. Now you take that thing and then you take the sine of that angle and then you divide the sine of the first angle by the sine of the second angle, and that is eccentricity. Now after that you have the parabola, which is basically an infinite ellipse. It's an ellipse with one focus at infinity. And if you think about that, as the eccentricity increases, the foci get closer and closer to the edge, to the end, and get farther apart from the middle. So if you are exactly at this angle here, your eccentricity is going to be 1, because it's the same angle, or not the same angle, but a special angle here. And then one focus is just at infinity. And parabolas and hyperbolas are open orbits. So they're escape orbits, or also collision orbits. But you can't stay stable in them. The hyperbola is just the linear slice out of the cone, I believe. Here, it produces two things, but in orbits there's only one because it's at one focus. And so those are the conic sections. And hyperbolas have an E that is greater than 1. Here I have a picture that I printed off, and it's a Creative Commons share-alike license picture. Anyways, now to determine the rotation of your orbit and the three different rotations that you can have in 3 dimensions. First, you need to define the reference plane, which is typically the equator. And then you can take the orbital plane, and the angle that is created at that intersection is the inclination, I. And then the line that is created at that intersection is the line of nodes, where the orbit itself intersects at. That's the ascending node at one part, where you're going above the orbital plane, and then when you're going down below it, it's the descending node. Now, how do you determine, though, the rotation on the 2 planes? Well, you need to pick a reference direction on the reference plane, which is typically the vernal equinox. So you take that direction, and the angle from that direction to the ascending node is the longitude of ascending node, which is that angle there. And then to determine the rotation in the orbital plane, you take the angle from the ascending node to the periapsis, which is the lowest point on the orbit. So from there, that's that angle, so then you can determine that. So if you want to determine where you are exactly right now, you need the true anomaly, which is the angle of your spacecraft or your planet from the periapsis in the orbital plane around like that. So that little V type thing, and the argument of periapsis is that little W type thing. And those are the orbital elements. A, semi-major axis, E, eccentricity, I, inclination, that the omega for longitude of ascending node, the squiggly W for argument of periapsis, and the V type thing for your actual location right then. So then if you know those things, and you know what time you launched your thing, or you have a set of observations for a reference time, you can find where it's going to be at and predict where your satellite is going to be or where your planet is. This is my video for the Kahn Academy Breakthrough Junior Challenge, and thank you for watching.